Hello everyone, my name is Rishabh and in this video we are going to discuss forward propagation of RNN. In the previous video we have discussed about the types of RNN. There we have seen three types of RNN. Those are one-to-many RNN, many-to-one RNN and many-to-many RNN. We have seen their architecture, like how information flows in them, and we have seen the real-world applications about them. Now we're going to see the forward propagation of RNN in this video. That is, we're going to take one example, which is the sentiment analysis example, and then we're going to see how the input transforms into output, how the hidden states are calculated. So by the end of this video, two things will be clear to us. Number one, why RNN are called recurrent neural network. What does recurrent stands here? And second is how RNN can retain the memory along the sequence. About this memory retention thing, we have already discussed in the first video, but that was a slight intuition about it. Now in this video, we're going to discuss in detail about the memory retention by deriving some equations of hidden states in the outputs. So I hope you all are going to enjoy this video. So let's start this video. So I hope this video will be useful to you. Let's jump into it.
Let's start this video with how to feed input to our recurrent neural network. To understand this, we'll be taking an example of sentiment analysis. So this is the example of sentiment analysis where we have sentences and the sentiment associated with each sentence. For example, if I pass this sentence as an input to our recurrent neural network, which is book is interesting, the recurrent neural network will give me an output as 1. That means positive. If I pass this sentence, it will give me an output as 0, that means negative. For this sentence, it will give me an output as 0, that means negative. But there's a catch here. We can't pass this sentence directly as an input to our recurrent neural network. You may ask why? Because this sentence is in the form of text, and our recurrent neural network or any neural network only understand numbers. So at first I have to convert this sentence in the form of numbers or vectors. To convert this sentence in the form of numbers or vectors, in NLP there are many ways. Let's understand one of the simplest way of converting any text into vectors. For example, say if I want to convert this sentence to a vector representation, how can I do it? At first, I have to convert this into tokens using a method called tokenization. Suppose here I am using word-wise tokenization, then this sentence will be splitted into separate word-wise tokens. Book is a token, is a token, interesting is a token. So first I'm going to convert this sentence into separate tokens. I'll be using word-wise tokenization. So there are 3 tokens I have. Now for each token, I have to apply vectorization, any vectorization technique to convert each token into vectors. So I'll be using one-hot encoding as a vectorization technique to convert each token into its vector representation. Now how the vectors will look like. Now we are using one-hot encoding as a vectorization technique. In one-hot encoding, the vectors will look something like this, 1 0 0 0 0, like this. That means the vectors will be sparse. It will not be dense, it will be sparse. Now, how to know what will be the length of the vector or what vectors will look like? For that, first we need to know the vocabulary of the corpus. What is corpus? All the sentences together in our data called as corpus. So this all sentences together are called as corpus. So in the corpus, first we need to know how many unique words are there in our corpus. Let's see. We have one unique word, book is interesting, book is taken, boring, book is not. So there are total of 5 unique word in our corpus. So vocabulary will be 5. Now what does this vocabulary represent? This vocabulary represent the length of the vectors. That means our length of the vector will be 5. Now with this 5 vectors, it will look something like the 0 0 1 0 or 1 0 0 0 0. The length will be 5. Now this vocabulary is 5. That means with this 5 vectors, with this 5 element of a vector, we can represent any word in our corpus. Suppose this book will look something like this, 1000. Is will look something like this. There are 5 elements. Vocabulary is 5, so there are 5 elements. Interesting will look something like this. Now you may ask that why I've put in the first place 1, and in is I've put the first place, in the second place I've given as 1. Why is it so? Because it depends upon the occurrences of the unique words. So book is the first unique word occurring, so it will be, so the first place in our vector is 1. For interesting, this is occurring in our as the third unique word, so all the words are 0, all the elements are 0 in this vector, and only the third element is 1. That means this vector will corresponds to interesting. Now with this vectors, book is interesting. Now wherever there is a book, it will be represented by this vector only. This all book is represented by this vectors only. So now we have successfully converted a text sentence into a vector representation. Now we can pass this input to our recurrent neural network. But wait, there is a format which we need to follow. So let's understand the input format which we need to follow to pass an input, to feed an input to our recurrent neural network. So our input format will look something like this. First, there will be a batch size. Second, there will be a sequence length, comma, third will be the input size. So now what is the batch size? Batch size will be the number of sequences or the number of sentences which is present in our entire corpus. So how many sequences, how many sentences are there? 1, 2, 3. 3 sentences are there. So the batch size will be 3. Batch size will be 3. Now what is sequence length? Sequence length is the number of time step which is present in a sequence length, or we can say in a sequence length which is of the maximum length. That is, in our case, we are having sequences or the sentences of unequal length. So we will take that sequence. By default, we take that sequence or sentence which is of the highest length. That is, we are going to take this one. Now number of timestamp, what does it represent? It represents the, suppose if I want to pass this sequence as an input, so how I am going to pass? I'm going to pass at timestamp t equals to 1, I'm going to pass this as an input. Timestamp t equals to 2, I'm going to pass this. Timestamp t equals to 3, I'm going to pass this. So sequence length represents the number of time step in each input sequence length. So we know we have a different input sequence length. So we are going to take that input sequence length which is of the maximum length. So I'm going to take this one which has 1, 2, 3, 4. 4 timestamp. Now in input sequence, this represents the number of features at each time step. That is, we know this is one time step t equals to 1, this is another time step t equals to 2, this is another time step t equals to 3. So what is the number of features here? Features are 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Every time step is having 5 features. So I'm going to have 5 here. So this is the input format which we need to follow to pass an input to our recurrent neural network. That is, first I'm going to have a batch size which represent number of sentences which are there in our entire corpus. Second, the sequence length, which is the sentence of maximum length. What is the sentence of maximum length? 1, 2, 3, 4. That is 4. Third is the input. That is, for each word, how many features are there, which is 5. Which is 3, 4, 5. So this is how we need to feed an input to our recurrent neural network. Now, let's move on to our main part of this video, which is forward propagation in RNN. To understand this, we are going to take the same sentiment analysis example. That is, we're going to pass this input, this sentence input, or if I say the vector representation of a sentence, which is this one, we're going to pass this as an input to our RNN, and we're expecting this output. And the input which we're going to pass will be at different timestamp. That is, at t equals to 1, we're going to pass this. At t equals to 2, we are going to pass this as an input. At t equals to 3, we are going to pass this thing. Before we understand the architecture, let us first see how the weighted connection will looks like. So let's say this is our neural network layer with 3 neurons. 1, 2, 3, 3 neurons. And these are the input. We know our input has 5 features. 1, 2, 3, 4, 5. So these are our 5 features. And we are taking our neural network to be fully connected. That is, each of these features will be connected to each of the neurons fully, like this. So what are these connections? What's the importance of this connection? So these connections are nothing but weights. And what does it signifies? It signifies the importance of the input in predicting the outcome. It will signifies the importance of each of these features in the input in predicting the outcome. So these are our input, which has the dimension 1, 5. This is the wi is what? Wi is our weighted input, which has the dimension 5, 3, 5 featured, 3 neurons. And then when the input goes through this neurons, there will be one more weighted connection for output. That is, each of these neurons will be connected to output like this. So this is the output connection WO, and its dimension is 3, 1. Now this is for a general neural network. We know we are dealing with recurrent neural network. So in recurrent neural network, it will have one more thing. That is, at every timestamp, we are going to pass information of the previous input back to the neural network at the different timestamp. That is, this will be h. Now we have seen that this a for input, to provide the importance of the input in predicting the outcome, we are having the weighted connection of the input. So this h will also have some importance in predicting the outcome. This will also influence the outcome. So it will also have some weights, which will be WH. Now the dimension of the WH will be 3, 3, because there are 3 neurons and we are passing back the same hidden state back to the same neurons. So it will be 3, 3. So this is the weighted connections of our recurrent neural network. Now let's understand the forward propagation by feeding the neural network, the same neural network, with different input at different timestamp. So let's simplify this architecture at different timestamp and how it will look like. So this is our neural network at, say, timestamp t equals to 1. and we are providing it with an input, say x1. And we know this x1 has some importance in predicting the outcome, and that importance will be specified by the weights, input weight, which is wi. So mathematically, what we are going to do with this wi, let me show you. What we are going to do is we are going to multiply this x1 with wi. That is, we are going to do dot product of the input with the wi, which is weighted input. In this step, this is input, this is weight. We are going to do a dot product of it, and we are going to pass it to our neurons, which is here. We are going to pass it to the neurons, which is here. Now in neurons, we know we have some activation function associated with the neurons, and in RNN the activation function by default is tanh. That is, this input will get a function of tanh. So it will become something like this: tanh of x1 wi. It will become something like this. So we have provided input, it get dot product with the weight, and then we know what we will get. We will get a hidden state h1, which we are going to pass in the next timestamp at t equals to 2 with different input x2. So what will be the equation for this h1 which we are going to pass? The equation of this h1 will be, let me write the equations. So the equations will be, first is h1. So the h1 will be tanh of x1 wi plus, there will be a bias because we are dealing with neurons, and in neurons we have some biases. So this will be a bias b. This will be a equation for h1. Now this h1 will get passed to this next timestamp with different input x2. Again, we know this x2 has some weight associated with it, xi, because this x2 will influence the output, so it has some importance, and that importance is specified with this weight. Similarly, this h1 will also have some importance, and that importance will be specified by wh. This dot product of this x2 wi and h1 wh will give us the output h2, which will be passed in the next timestamp to the same neural network, which will be passed at the next timestamp t equals to 3 to the same neural network with different input x3. That is, h2 will look something like this: tanh of this thing, dot product of x2 w1 wi and h1 wh, dot product of x2 wi plus h1 wh plus a bias b. This will be the equation for h2, and this h2 has been passed to the next timestamp with a different input x3, and x3 will also have some weight wi. Now in this here, what will happen? So what is this x1 x2 x3? What are this x1 x2 x3? We've already seen that this x1 is nothing but book, x2 is nothing but the vector representation of is, x3 is nothing but the vector representation of this last word, which is interesting. Now we have come to the last word of this sequence. Here, what we are expecting, at the last word we are expecting an outcome, because we are dealing with a sentiment analysis, and in sentiment analysis we know it's a type of many to one RNN where we are providing many as an input. That is, as a sequence we are providing an input, and output is 1, many to 1, right? Many, that is, input is a sequence and output is 1, that is, we are going to have only one output. So here we are going to have an output. So in the last step, where we are last word, after the last word we are getting the output. That is, at the last timestamp t equals to 3, we must get an output O. Okay, we are getting the output at the last timestamp O. So here also we will be calculating h3. h3 will be what? Tan h of dot product of this and this. That is x3 wi plus h2 wh plus a bias b. Now we know we don't have any further timestamp, we don't have any further input. So this h3 will be contributed to provide us the output O. That is, this h3 will be passed and it get multiplied with the weighted connection of output, that is this one. So we are at this step. We have provided all the input at different timestamp, at one timestamp, and we are at this step. Now this WO get multiplied with the last hidden state H and we get the output O. So output O will look something like this. O will be H3, which is this one. It get dot product with the output weight WO, output weight WO, plus a bias B0, because we know output is also a neuron which has some bias, which is B0. So this is the output O. So this was about the forward propagation of RNN. This is how the information flows in the RNN. And these are the equation which we have derived from the forward propagation of RNN. Now here, two things are cleared. First is why we call RNN, why we call this neural network which we have drawn, a recurrent neural network. Why we called it a recurrent? The word recurrent means occurring repeatedly. And we have seen here that this neural network is occurring repeatedly. The same neural network is occurring repeatedly at different timestamp t1, t2, t3. That is the reason why it is called as recurrent neural network. And by this, and because this neural network are same at different timestamp, so the weights associated are also same. We are using the same weights. You can see at each of this h1, h2, h3 which we have got, we are using the same weights, wi, wi, wi. We are using the same weights. So here a concept comes of parameter sharing. In RNN, there is a concept of parameter sharing. Second important thing which is cleared from this forward propagation is why we use RNN for sequential data. In the previous videos also, we have seen that we use RNN for sequential data because it has the ability to store memory. It has the ability to retain memory. And from this equation, it is clear that how it has the ability to retain memory. Like for example, we know if we provide an input x1, we get a hidden state h1 which we pass to the next timestamp t equals to 2 with a different input x2. That is, at this timestamp, this x2, at this timestamp, at second timestamp, we are providing x2 and the information of the previous input through h1. And this is clear from this equation also. That is, this h2 we are passing has the information of x2 directly and also has information of h1. It has a component of h1 and h1 has the information of x1. That is, like this, information will be retained along the sequence. So the output which we will be getting will be based on all the previous input. You can see this output O has a component of h3, and we know h3 is taking x3 and a component of h2. h2 is taking x2 and a component of x1. This h1 is taking x1. So directly and indirectly, this O is taking into account all the previous input x1, x2, x3. So this O is taking the information of all the previous input to produce the output O. That is, the output which we will be getting will be contextually correct. It will maintain the context of the previous inputs. This is how memory is retained along the sequence in RNN. So this was about the forward propagation in RNN. Okay, one more thing I need to mention is, you can see here, except t equals to 1, every other timestamp is taking two input into consideration, which is x2, h1, h2, x3. But this t equals to 1 is taking only one input x1. To maintain consistency, what we are going to pass? We are going to pass a pseudo input or an input of zero weight, of an input of zero vector. This h0 is nothing but a zero matrix or a zero vector. So this will become, the equation will slightly change and it will become h0wh plus a bias b, just to maintain the consistency. Now, before we end this video, let's discuss one more important thing about the forward propagation in RNN, which is total number of trainable parameters. When we say total number of trainable parameters, we are referring to weights and biases. In our case, we are taking an input of dimension 1, 5, a neural network with 3 neurons, and a output, this one output. For this, we are getting weights as wi plus wh plus wo with sum up to this 5 3, this is 5 3 which is 15, this is 3 3 which is 9, this is 3. So this, they all sum up to 27. For number of biases, we know each neuron will have a bias. So there are 4 neurons, 1, 2, 3, and for output 1. So there are 4 biases here. So these are total number of trainable parameters in our forward propagation in our case, which is weights 27 and biases 4.